Hi everybody, Mrs. Bowen here, and we're going to take a look at guided notes for Standard 23 Pythagorean theorem. And this theorem tells us the relationship between the three sides in a right triangle. So the triangles that we'll look at today have to be right triangles, meaning that one of the angles forms a 90-degree right angle, which is why we see the square tick marks. If we look at the figure on the left, we can use this to talk about what this theorem tells us. So we can see we have three side lengths listed here. Our shortest side in the triangle is 3, the next in length is 4, and the longest side is 5 units. And then along the sides of the triangle, we have these squares here, these squares with little unit increments. And what this is depicting is if we were to look at this shortest side length here of 3, and we were to square it and do 3 squared, or 3 times 3, and we're literally building a square here that's 3 by 3, or 3 times 3, well, 3 squared is 9, and when you have a 3 by 3 square, you get an area of 9. So that's what this is depicting here, the square. When we look at this side length, 4 squared, or a 4 by 4 square, gives us here the area of 16. And on our longest side, 5 squared, or 5 times 5 here is giving us an area of 25. So take one moment, and I'd like you to look at the 3 areas of the squares that you see. Do you notice a relationship between our 3 squares of 9, 16, and 25? If you look at 2 of the squares and compare them to the 3rd square, do you see a relationship? You may notice, maybe you picked up on it here, that the sum of my 2 smaller squares, 9 plus 16, equals 25, my bigger square. And that's exactly what the Pythagorean theorem tells us. It tells us that the sum of the 2 smaller squares equals the big square. And we'll talk about how you know the 2 smaller squares and how this right angle comes in and some terminology here in just a moment. Let's real quick look at the figure on the right, and I want to see if you can think backwards. What if I told you that A's side length was 6, B's side length was 8, and I'm asking you, what is C's side length? What must C be? Well, we could use similar reasoning, and if A's side length on this triangle is 6, then we could find the area for this square right here. And 6 squared, or 6 times 6, would give us 36 units squared. We could do the same thing to find the area of this square. 8 times 8 would here give us an area of 64 units squared. And so then, in order to find this side length C, we could find the sum of the 2 smaller squares. 36 plus 64 actually gives us 100. So our area of this square must be 100 units squared. And we can think backwards here. If we know the area is 100, we could take the square root of 100. And then we would find that C, the square root of 100, is 10. C must equal 10. So here we see that the sum of the smaller squares is equal to the bigger square. Let's talk about the Pythagorean theorem just looking at a triangle and without having to draw the squares along the edges of the triangle. So we can use some letters to help us talk about this. And if we're using letters, I'm going to represent my smaller squares here. So I'm going to say A squared plus B squared. The sum of my smaller squares is equal to my big square. And I'm going to introduce some new terminology here. So A and B, those sides are called your legs. And when you look at the triangle, the 2 sides that form the right angle, those are your legs. Those have to be the legs. So here I can say A is a leg and B is a leg. formed by my right angle. And then the longest side, or the side that is across from your right angle, this is something called the hypotenuse. Hypotenuse, and I'll make a note here that it's our longest side. It's also the side that is across from the right angle. I often abbreviate hypotenuse as hype. And so my longest side here is the hypotenuse. And so in any right triangle, we can find the right angle, and the two sides forming the right angle are the legs, and the longest side is our hypotenuse. We can find the squares of the two legs and add them together or find their sum, and it will always be equal to our longest side, the hypotenuse, squared. So Pythagorean theorem is a squared plus b squared equals c squared, and this works again for right angles, and keep in mind c has to be your hypotenuse, the longest side that is across from the right angle. So let's use this theorem that we learned to try 3 examples. Example A says find the missing side of each right triangle, and then we're asked to find the perimeter. So in example A, I can find my right angle, and the side across from it, that has to be my C, or my hypotenuse. That has to be my C. And I can see that right here, I'm missing this leg. So I could make a note that for this first example, I'm missing a leg. And I'm going to write my Pythagorean theorem. That will be helpful. I have a squared plus b squared equals c squared. And then I can fill in the parts. So I'm missing a leg. I'll call that A. And it doesn't matter which leg you say is A and which leg you say is B. The piece that matters is that your hypotenuse has to be C. So because I don't know this leg, I'm just going to call it A. So I'll have a squared plus, then I can look and identify my other leg, B, and here it's the 12 meters. So I'm going to plug in 12 for B. So now I have 12 squared equals my C squared, which is my hypotenuse. So I'm doing 13 squared. So now I have an equation. I only have one variable, and I'm going to have to do some squaring here. So I'll have a squared plus 12 squared is 144. 13 squared is 169. Keep in mind, 13 squared is saying 13 times 13, or you can use your calculator and type 13 raised to the second power. I almost have this a squared by itself, but I need to move this positive 144 over to the other side. So I can subtract 144 from both sides, and I'll get a squared equals 169 minus 144 gives me 25. And then my last step here, and we've talked about this recently, if I want to undo something squared or something raised to the second power, I can take the square root of both sides. And when I do that, I'll get that a equals 5. Square root of 25 is 5. So that means my missing side, in this case my missing leg, was 5 meters. And then I can use that to help me find the perimeter, now that I know that this missing piece was 5 meters. Perimeter means we add up all the sides. So I can do 5 plus 12 plus 13. And when I add those up, I'll get a perimeter of 30 meters. Let's look at example B. In example B, I find my right angle. And the side that is across from my right angle is always the hypotenuse, or it's always my C. So in this problem, I'm missing the hypotenuse. I'm going to say missing the hype. So I can use these other two as my legs. It doesn't matter which I say is A and which I say is B. I'll write my formula, my Pythagorean theorem, a squared plus b squared equals c squared. And then I'm going to plug in what I know. So I know that one of my legs here, A, I'm going to say is 16. So I'll have 16 squared plus my b, which is the other leg, 30, plus 30 squared equals, and I don't know my hypotenuse. That's what I need to find. So for c, I'm just going to call it c squared. I have one variable here. And so now what I can do in my calculator, I can do 16 squared plus 30 squared and see what I get. I'll get 1,156 equal to c squared. I want to undo c raised to the second power because I don't want c squared or the hypotenuse squared. I just want the hypotenuse. So I can do that by taking the square root of both sides, and then I'll get c by itself. And when I take the square root of 1,156, I get 34. So that means that my missing side, in this case, the hypotenuse here, was 34 meters. And then I can use that to help me find my perimeter. So for perimeter, I will add up my three sides. So I have 16 plus 30 plus 34. When I add those up, I get 80 meters for my perimeter. Example C, find my right angle. The side across from my right angle, the longest side here is my hypotenuse, so the 30 feet is my C. So I'm missing a leg. I'm going to write my Pythagorean theorem. A squared plus b squared equals c squared. And then I'm going to fill in what I know. So I'm missing a leg. I'm going to let that be my a. I don't know it. So I have a squared plus my other leg. So 24 I'm plugging in for b. Equals my hypotenuse squared. And my hypotenuse we said is 30. So I'm plugging in 30 for C. Now I can do these squares in my calculator. So I'll have a squared plus 24 squared gives me 576. 30 squared gives me 900. Now I can move 576 to the other side by subtracting it. So I'll subtract 576 from both sides, and I'll be left with a squared equals 900 minus 576 is 324. And then to undo a squared, I can take the square root, and I'll get a equals 18. So I found that my missing side, in this case, a leg, is 18 feet. And then for my perimeter, I'm going to add up the three sides. So I'll have 18 plus 24 plus 30. And that will give me a total perimeter of 72 feet. Notice that in these three examples, my missing side ended up being a whole number, but that's not always the case. Sometimes when you end up taking the square root, we get decimals, and that's fine. These are side links, so they don't always have to be a whole number. They can definitely include decimals. So keep that in mind. And right now, we have 3 U-tries. So go ahead, pause the video, and see what you come up with. Let's see how you did. On the first U-try, I was missing a leg, and so I found that that missing leg was 12 inches, perimeter was 36 inches. The second U-try, I was missing my hypotenuse, the longest side across from my right angle, and I found that that missing hypotenuse was 5 miles, perimeter was 12 miles. And the third U-try, I got some decimals. I was missing my leg here, and I found that that missing leg was 11.7 inches, and the perimeter was 32.8 inches. So now that we know about Pythagorean theorem and we know that it only works for right triangles, let's see if we can make some classifications on the back side about some other types of triangles. So we have a GeoGebra exploration here, and you're going to use the GeoGebra sliders activity to help you answer these two questions. And as you're doing the GeoGebra exploration, you're going to try to fill in this table. So the first question you're going to try to answer is, how would you classify this triangle, so a triangle with these 3 side lengths, based on its angles? So looking at the measures of its 3 angles. And the second question you're going to answer is, how does the sum of the smaller squares compare to the bigger square? And you'll answer that for these 3 triangles. Here is the GeoGebra sliders activity that we'll use to help us with this exploration. And on Schoology, by where you see the guided notes video, you'll see a link that is titled Pythagorean Data. That's the link you need to click on to get to this website. Once you get to this GeoGebra website, the reason I call this activity a sliders activity is because we have these sliders over here that we can adjust to change the side lengths of our triangle. And so the first triangle we need to look at is a 6, 8, 10 triangle, or in other words, it has side lengths of 6 meters, 8 meters, and 10 meters. And so I've created the triangle, and I can now spin it around so that I can observe what is happening with the different angles. And I see that I've got some areas, it looks like here. So if we're looking at this green square here, this side length would be side length B, and we're doing B squared, just like we talked about in our notes. To get the area of this green square is 64. But the first question we need to answer in our table is, how can we classify this triangle based on its angles? And if you recall, there's 3 ways to classify triangles based on angles. It could be an acute triangle, an obtuse triangle, or a right triangle. And this triangle here has one angle that's 90 degrees, one angle that's about 37 degrees, and one angle that's about 53 degrees. So because we have one angle that is 90 degrees, it has a right angle, this would be classified as a right triangle. The second question we have to answer in our table is, how does the sum of the smaller squares, or my sum of my purple and green square, compare to my larger or bigger square, which is the red square? So we can look here. The sum of my smaller squares would be 36 plus 64, and I get 100. And that actually is equal to my bigger square, which is also 100. So here we could say the sum of the smaller squares is equal to my bigger square. That's what we have noticed in this case. I helped you with your first triangle. Now you will need to use this GeoGebra activity to do the second 2 triangles. So my next triangle is a 7, 8, and 9 are my side lengths. And so you will need to create this triangle, observe what is true about the angles in order to classify the triangle, and then notice what must be true when you look at the relationship between the sum of the smaller squares compared to the bigger square. So at this time, you're going to go ahead, pause the video, and finish filling out your table for your exploration. Let's see what you come up with. Here's what I wrote down during my GeoGebra exploration. My first triangle had side lengths 8, 10, and 6, and notice that I rewrote them going from smallest side length to longest side length, so 6, 8, 10. And for this triangle, I found that it was a right triangle, and we could classify it as a right triangle because it had one 90-degree right angle. When we were comparing the sum of the smaller squares to the bigger square, they ended up being equal. 6 squared was 36, 8 squared was 64, 10 squared was 100, and we found that they were equal. For my second triangle, I rewrote them again. For a 7, 8, 9 triangle, I found that I could classify it as an acute triangle because all 3 of its angle measures were less than 90 degrees. When I compared the sum of the smaller squares to the bigger square, I found that the sum of the 2 smaller squares was greater than the bigger square. And then for my last triangle, it was a 4, 8, 10 triangle. It was an obtuse triangle because it had one obtuse angle, or one angle that was between 90 and 180 degrees. When I compared the sum of my 2 smaller squares to the bigger square, I found that the sum of the 2 smaller squares was less than my bigger square. So let's use this exploration to help us make some predictions. So on example D, we have 3 different side lengths of my triangle, and I'm going to try to compare the sum of the smaller squares to the bigger square to make a comparison. So I first need to find my 2 small sides, and in this case it would be the 5 and the 12. So I can do 5 squared plus 12 squared and compare it to my bigger square, 14 squared. When I do 5 squared plus 12 squared, I get 169. And when I do 14 squared, I get 196. And so we can notice 169 is less than 196. And if we look up here at the top, here we're saying that the sum of our smaller squares is less than the bigger square. And we classified that as obtuse. So this would be an obtuse triangle. The way I actually like to think of it is that you're always observing your bigger square or the biggest side squared. And so you're observing your c squared, if you think of it that way. When I'm thinking of it that way, if I'm observing the bigger side squared, here I can see that my c squared is bigger, which makes it obtuse. In example E, I need to pick my 2 smallest sides, so that'd be the 5 and the 12. So I'm doing 5 squared plus 12 squared, actually again, which we just said is 169, and I'm comparing it to 13 squared. So notice I'm not putting an equal sign or an inequality sign here because I first need to figure out the relationship before I can put a sign there. 13 squared gives me 169. Well, those are equal. And when the sum of the smaller squares is equal to the bigger square, we learn that it's a right triangle. Example F, my 2 smaller sides would be 9 and 14. So I'm doing 9 squared plus 14 squared, comparing it to my bigger square, 15 squared. 9 squared plus 14 squared gives me 277. 15 squared gives me 225. I like to think of it as I'm observing what's happening to my bigger square, or my c squared. And I see 225 here is less than my smaller squares. 225 is less than 277. And so this would be an acute triangle. Let's write some Pythagorean inequalities, or let's come up with a generic way to write these rules. And instead of using numbers, let's use some letters. So one way I could write it, and we just learned on the front side the Pythagorean theorem, and that has to do with right triangles, we said. So we could say when a squared plus b squared equals c squared, or when the sum of the smaller squares equals the bigger square, then it's a right triangle. Keep in mind a right triangle has one right angle, one 90-degree angle. When the sum of our smaller squares is greater than our bigger square, and again, this is a greater than sign. And I always like to observe what's happening to my c squared, or my bigger square. So when my bigger square is smaller, then it's an acute triangle, something like that. Remember, an acute triangle has all 3 angles less than 90 degrees. Each of them less than 90. And then the last type of inequality relationship here, when we compare the sum of the smaller squares to the bigger square, and the bigger square is larger, or if we were to say this inequality sign, we're saying the sum of the smaller squares is less than our bigger square. Here we get an obtuse triangle. And with an obtuse triangle, keep in mind one of your angles here has to be a big obtuse angle, meaning this angle is between 90 degrees and 180 degrees. Again, I like to observe what's happening to my c squared, or my bigger square. When my bigger square, or when c squared is equal, it's a right triangle. When c squared is smaller, it's the smaller number, then it's an acute triangle. And when c squared is bigger, or it's the bigger number, it's now an obtuse triangle. So using these Pythagorean inequalities, you have 6 you tries to do. Make sure you are not necessarily assuming that the first two side lengths given are your smaller side lengths, right? So you need to identify the smaller side lengths to begin with. At this time, go ahead, pause the video and see what you come up with. And here you can check how you did on these last 6 U-tries. Take a moment, look at the inequality statements and at how you classified the triangle. Notice in U-try 4, my c² was bigger, so it was an obtuse triangle. U-try 5, my c² was equal, so it was a right triangle. U-try 6, my c² was smaller, so it was an acute triangle.